Hey everyone, and welcome back to another episode of the show. I'm your host, Zoe, and today we are diving into a question that I think pretty much everyone who has ever tried to run an AI model on their own machine has asked themselves at some point. GPU, RAM, or CPU, what actually matters most for AI? And to help me figure this out, I have a very special guest with me today. Joe, welcome to the show, man.
Hey Zoe, thanks for having me. Super excited to be here.
So, Joe, for the people who do not know you yet, and honestly, I'm sure most of our listeners already do because you're kind of a regular in the AI dev community, but give us a quick intro. Who are you? What do you do? And how did you get into this whole AI thing?
Sure. So my name is Joe. I'm a freelance software developer based in Berlin originally, but I work with clients all over the world. I have been coding for about 10 years now, mostly web stuff, full stack, JavaScript, TypeScript, React, Node, the usual suspects. But about 3 years ago, I started getting really deep into AI and machine learning. Not like building models from scratch, but integrating AI into real applications. So taking existing models, making them work in production, connecting them to APIs, that kind of thing.
So, you are like the bridge between the pure AI research world and actual working software that people use.
Exactly. I mean, researchers build incredible things, but someone has to make them actually usable, right? And that is where I come in.
Love that. Okay, so let us jump into the deep end. GPU, RAM, CPU. If someone comes to you and says, "Hey Joe, I want to run AI stuff on my machine. What do I need to prioritize?" What do you tell them?
Honestly, the first thing I ask them is what kind of AI are we talking about? Because the answer changes dramatically, depending on whether you want to train models from scratch, run inference on existing model, or do something like data preprocessing. These are completely different workloads.
Okay, fair point. So let us break it down. Let us start with the GPU because I feel like that is the sexiest component right now. Everyone is obsessed with GPUs.
Oh, for sure. The GPU is absolutely the rock star of the AI world, and for good reason. When people think about AI hardware, they think about NVIDIA and those massive data centers full of H100s and now Blackwell chips.
Right. And those things cost like $30,000 a piece or something insane.
Yeah, the pricing is wild. But here's the thing, the GPU is so important because of how AI models actually work under the hood. The core operation in neural networks is matrix multiplication. You have these huge matrices of numbers and you're multiplying them together over and over and over again.
And GPUs are just built for that kind of parallel computation.
Exactly. A CPU is incredibly powerful, but it has maybe 8 or 16 cores. A modern GPU has thousands of cores. An NVIDIA RTX 4090 has over 16,000 CUDA cores. So when you need to do the same mathematical operation on millions of numbers at the same time, the GPU absolutely destroys the CPU.
So if I want to train a model from scratch, GPU is the answer.
100%. Training is where the GPU shines brightest. When you train a model, you're doing forward propagation and backward propagation across potentially billions of parameters. Doing that on a CPU alone would take weeks or months for any reasonably sized model. A good GPU brings that down to days or even hours.
But what about people who are not training models? What about people who just want to run existing models like Llama or Mistral locally?
That is inference, and it is a different story. For inference, the GPU still helps a lot, especially for large language models, but the bottleneck often shifts to something else.
Let me guess, RAM?
Bingo! Well, specifically VRAM, the memory on your graphics card, and I think this is the most misunderstood component in the AI space right now.
Okay, talk to me about VRAM. Why is it so critical?
So every AI model has a certain size. When you load a model like Llama 3.170 billion parameters, that model takes up a specific amount of memory. The weights themselves are the parameters stored as numbers. In 16-bit precision, that is about 140 gigabytes of memory just for the weights.
Wait, 140 gigs just for the weights? That is insane.
Right? And that is just to load the model. You also need additional memory for the context window, the key value cache, and the activations during generation. So realistically, you need even more than that.
So if I have an RTX 4090 with 24 gigs of VRAM, I cannot even run that model.
Not in full precision, no. You would need to use quantization to shrink the model down. With 4-bit quantization, you can fit that 70 billion parameter model into about 35 gigs of VRAM. Still does not fit on a 4090, but it fits on something like an A100 or two 4090s.
So VRAM is literally the gatekeeper for what models you can run.
Exactly. I tell people all the time if you're buying hardware specifically for AI inference, do not just look at how fast the GPU is. Look at how much VRAM it has. A slower GPU with more VRAM can run models that a faster GPU with less VRAM cannot even touch.
That is such a good point. So what about regular system RAM, like the DDR5 sticks in your motherboard?
System RAM matters too, but in a different way. When you run AI workloads, you're constantly loading and unloading data. Your datasets need to be held in memory. Pre-processing pipelines shuffle data around. And if you do not have enough system RAM, your computer starts swapping to disk, which is brutally slow.
So system RAM is more about the data pipeline around the AI work.
Exactly right. Think of it this way. Your system RAM holds your dataset, your pre-processing code, and the operating system. Your VRAM holds the model weights and the immediate computations. They work together, but they serve different roles.
And what about scenarios where you do not have enough VRAM but you have plenty of system RAM? Can you offload?
You can, and this is becoming more common. There are techniques like CPU offloading where parts of the model live in system RAM and only get moved to the GPU when needed. Llama.cpp does this really well. You can run a 70 billion parameter model on a machine with 64 gigs of system RAM and no GPU at all if you're patient.
But it is slow, right?
It is slower? Yeah. Like we are talking maybe 1 or 2 tokens per second versus 50 or more on a good GPU. But here's the thing, it works. And for a lot of hobbyists or people who just want to experiment, that trade-off is totally acceptable. You do not need to drop $5,000 on a GPU to start playing with AI.
That is actually huge. I think a lot of people feel like they cannot even get started without expensive hardware.
And that is a misconception I really want to bust. You can run so many interesting models on just a CPU with enough RAM. The smaller Llama models, the Phi models from Microsoft Mistral 7B, these all run on consumer hardware.
Okay, so we have covered GPU and RAM. Where does the CPU fit into all of this? Is it just the dumb workhorse that loads data?
Not at all. The CPU is doing a ton of critical work. First of all, data preprocessing and loading. Before you ever touch a GPU, you need to clean your data, tokenize it, batch it up, and get it ready. That is all CPU work. If your CPU is slow, your GPU sits idle, waiting for data, which is a huge waste.
So the CPU can actually become a bottleneck.
Absolutely. In fact, one of the most common performance issues I see in production AI systems is not that the GPU is too slow, but that the CPU cannot feed data to the GPU fast enough. People spend thousands on a top-tier GPU and pair it with a mediocre CPU, and they wonder why their utilization is stuck at 30%.
That is such a classic mistake. So what would you recommend for a balanced build?
It depends on your use case, but generally I would say do not cheap out on any of the three. For a dedicated AI workstation, something like a Ryzen 9 or Intel Core i9 with at least 64 gigs of system RAM, and then the best GPU you can afford with as much VRAM as possible.
What about people who are doing fine-tuning versus people doing inference versus people doing both?
Great question. For fine-tuning, you really want the GPU to be your priority. Fine-tuning involves actual training, even if it is just a few epochs. You will be doing forward and backward passes through your model. So GPU compute and VRAM are both critical. For pure inference, VRAM is actually more important than raw compute speed, in my opinion. And for data preprocessing or traditional machine learning like scikit-learn stuff, a good CPU and plenty of system RAM will take you very far.
What do you think about the cloud versus local debate? Because a lot of people argue that you should not buy hardware at all and just rent GPUs in the cloud.
I think both approaches have their place. Cloud is amazing for flexibility. You can spin up an instance with 8H100s, run a training job for a week, and then shut it down. You pay for exactly what you use. For many businesses, that is the smartest move.
But you're a local hardware guy, you're not you?
I just love having my own machine for development and experimentation. Local is so much faster. The iteration cycle of making a change to your code and immediately seeing the result versus uploading to the cloud, waiting for the instance to start and then running it. That time adds up. Plus, for privacy-sensitive work, you might not want to send data to a cloud provider.
Privacy is a huge one, actually. If you're working with medical data or financial data or just personal stuff, you might not want it leaving your machine.
Exactly. And with models getting smaller and more efficient all the time, local AI is becoming more and more viable. Look at what Apple is doing with their neural engine and unified memory. Look at the new Ryzen AI chips from AMD. The trend is clear. AI is moving to the edge.
Speaking of Apple, the whole unified memory architecture thing, can you explain that for people who do not know?
Sure. So traditionally, you have separate memory for the CPU and the GPU. Your system RAM and your VRAM are physically different pools of memory. Data has to be copied from one to the other over the PCIe bus, which creates latency and bottlenecks. Apple Silicon uses a unified memory architecture where the CPU and GPU share the same pool of memory.
So if you get a Mac with 128 gigs of unified memory, your GPU can use all of that?
Exactly. That is the killer advantage. A Mac Studio with 128 gigs of unified memory can run models that would require multiple expensive NVIDIA GPUs because the VRAM limitation simply does not exist in the same way. The GPU just uses the same memory pool. It is brilliant for AI workloads.
But I have heard people say the compute performance is not as good as NVIDIA.
That is true for training. For training through Apple GPUs, they are competitive, but NVIDIA still leads, especially with CUDA and all the software that has been built around it. But for inference, Apple Silicon is incredibly efficient. The combination of large unified memory and good performance per watt makes it a really compelling option.
So if someone asked you today, Zoe, I want to get into AI, what computer should I buy? What do you say?
I would say it depends on your budget and your goal. If you have around $2,000, get a Windows or Linux machine with an NVIDIA RTX 4070 or 4080. 12 to 16 gigs of VRAM, 32 gigs of system RAM, and a solid mid-range CPU. That will let you run most open source models, run inference comfortably, and do some fine-tuning.
And if you have a bigger budget?
If you have $5,000 or more, look at an RTX 4090 build, or even consider a used RTX 3090, which gives you 24 gigs of VRAM for much less money. Or go the Mac route with a Mac Studio with 64 or 128 gigs of unified memory.
And if you're broke like me?
Then start with what you have seriously. If you have a laptop from the last few years, you can run so many things. Use Google Colab for GPU access. Run smaller models with Ollama or Llama.cpp. Use cloud credits from Google or AWS. The barrier to entry has never been lower.
I love that. Okay, let us get a bit more technical for a second. What about the actual architecture of these models? Like what makes them need so much memory?
Great question. So a neural network is essentially a series of layers. Each layer has weights and biases. When you multiply an input by these weights, you get an output. The more parameters a model has, the more layers and the more weights per layer. Each weight is a number that needs to be stored in memory.
And the precision of those numbers matters, right?
Hugely. If you store weights in 32-bit floating point, each weight takes 4 bytes. In 16-bit, it is 2 bytes. In 4-bit, it is half a byte. So going from 32-bit to 4-bit reduces your memory requirement by 8 times. That is why quantization is so powerful.
But does quantization hurt quality?
It can, but modern quantization techniques are incredibly good. The difference between a 16-bit model and a 4-bit model is often barely noticeable for most tasks. There are benchmarks showing that a 4-bit version of Llama 3 scores within a couple of % of the full precision version on most evaluations.
So you're trading a tiny bit of accuracy for a massive reduction in memory usage?
Exactly. And for most real-world applications, that trade-off is absolutely worth it. Unless you're doing scientific research where every decimal point matters, quantization is the way to go.
Let us talk about batch size for a second, because I think that is another place where VRAM becomes critical.
Oh yeah, batch size is a huge factor. When you train a model, you do not process one piece of data at a time. You process a batch of 8 images or 16 text samples or whatever. The larger your batch size, the more VRAM you need because you have to hold all those intermediate computations for every item in the batch simultaneously.
So more VRAM means larger batch sizes, means faster training.
Up to a point, yes. Larger batches can train faster because you're processing more data per step. But there are diminishing returns. Very large batches can actually hurt model quality because the gradients become less noisy and you can converge to sharp minima that do not generalize well.
Interesting. So it is not just about throwing hardware at the problem.
Never is. Software and technique matter just as much as hardware. Gradient accumulation is a great example. You can simulate a large batch size by accumulating gradients over several smaller batches. That lets you effectively use a larger batch size than your VRAM would normally allow.
So there are always workarounds.
Almost always. Mixed precision training is another one. You use 16-bit for most computations and only keep critical things in 32-bit. That cuts memory usage nearly in half with no quality loss. Models like Stable Diffusion and Llama were trained with mixed precision.
Okay, let me ask you this. What about inference specifically for large language models? What is the bottleneck there?
For LLM inference, the bottleneck is usually memory bandwidth. Here's why. When you generate text, you're doing it autoregressively. You generate one token at a time. Each token requires a forward pass through the entire model. But the actual computation per token is relatively small compared to moving the model weights from memory into the compute units.
So you are memory bandwidth bound, not compute bound.
Exactly. The GPU has to load all those billions of weights from VRAM into the CUDA cores for every single token. The speed at which it can do that is limited by the memory bandwidth of your GPU. That is why an RTX 4090 with its massive memory bandwidth generates tokens so much faster than an older GPU, even if the older one has similar compute.
So for LLM inference, memory bandwidth is actually more important than raw flops.
In my experience, yes. And that is also why Apple Silicon does so well at inference. The unified memory architecture gives incredible bandwidth. The M2 Ultra has over 800 gigabytes per second of memory bandwidth. That is competitive with high-end NVIDIA GPUs.
So if I'm building a system for running LLMs locally, I should prioritize memory bandwidth in my GPU choice.
Absolutely. And make sure you have enough VRAM to fit the model you want to run. Those are the two most important specs. Compute performance is secondary for pure inference workloads.
What about running multiple models at the same time or serving models to multiple users?
That is where things get really interesting. For serving, you need to consider throughput. How many tokens per second can your system generate across all users? And that depends on batching. You can batch multiple user requests together to improve utilization, but larger batches need more VRAM. So again, VRAM is the limiter.
So the theme here is that VRAM is the unsung hero of AI hardware.
I think that is fair to say. Everyone talks about GPU compute and teraflops, but in practice for most AI workloads, especially inference and fine-tuning VRAM, is what determines what you can actually do.
Let me play devil's advocate here for a second. What about the rise of really small models, like Microsoft Phi 3 Mini, which has only 3.8 billion parameters and runs on a phone?
That is a great counterpoint. Small models are changing the equation. If you only need a model for specific tasks, a small model can be incredibly effective and runs on almost any hardware. Phi 3 Mini Llama 3.21b and 3B Gemma 2.2b. These models punch way above their weight class.
So the trend is towards efficiency.
Huge trend. The research community is putting massive effort into making models smaller and more efficient. Distillation, quantization, pruning, architecture search. All of these techniques are making it possible to run capable models on commodity hardware.
So do you think in 5 years we will still be obsessing over GPUs and VRAM?
I think we will care less because the hardware will have caught up and the models will be more efficient. But also, new, more capable models will push the boundaries again. It is an arms race. As soon as we can run Llama 3 on a phone, someone will release a model that needs a data center again.
The AI hardware treadmill never stops.
It really does not. But that is what makes this field so exciting. There is always a new challenge.
Okay, I want to talk about something practical. Let us say I'm a web developer like you used to be. I know JavaScript and React. I want to add AI features to my app. What do I need hardware-wise?
Honestly, for most web developers, you do not need to worry about hardware at all, because you will be using APIs. You call the OpenAI API, or the Anthropic API, or the Google API, and all the heavy lifting happens on their servers. Your laptop is perfectly fine for building AI-powered applications.
So the hardware conversation is really for people who want to run models locally.
Exactly. If you're happy using APIs, and most people should be, you do not need to think about any of this. The API providers handle all the GPU infrastructure. You just pay per token.
But there are reasons to go local, right?
For sure. Cost at scale, if you're doing millions of requests per month local, can be cheaper. Latency local is almost always faster. Privacy, your data stays on your machine. And customization, you can fine-tune models for your specific use case.
So the decision tree is something like if you're prototyping, use APIs. If you're scaling or have privacy needs, go local.
That is a really good way to think about it. And you can also do hybrid approaches. Use APIs for the heavy lifting and local models for things that need low latency or handle sensitive data.
Let us talk about some real numbers for a second. What kind of performance difference are we talking about between running on CPU only versus GPU?
It is dramatic. A modern GPU can be 50 to 100 times faster than a CPU for training workloads. For inference, the gap is smaller but still significant. Running a 7 billion parameter model on a CPU might give you 5 tokens per second. On a GPU, you can get 50 to 100 tokens per second.
That is the difference between painful and smooth.
Exactly. 5 tokens per second is usable if you're patient. 50 tokens per second feels like a natural conversation. That is the threshold where AI starts to feel magical rather than frustrating.
What about the difference between different tiers of GPUs, like a 4060 versus a 4090?
For training, the gap is massive. The 4090 has about 2.5 times the compute performance of the 4060. But for inference, the gap is smaller if the model fits in both cards' VRAM, because you are memory bandwidth limited. The 4090 has about 1.7 times the memory bandwidth of the 4060, so you get roughly 1.7 times the inference speed.
So even a budget GPU gives you most of the inference benefit.
If the model fits, yes. And that is a big if. The 4060 has 8 gigs of VRAM. That limits you to smaller models. The 4090 with 24 gigs can run much larger models. So the VRAM difference is actually more impactful than the compute difference in many scenarios.
This has been incredibly helpful, Joe. I want to ask you one more thing before we wrap up. What is the most common mistake you see people make when they are building an AI-capable machine?
The most common mistake is spending way too much on a CPU and not enough on the GPU. I see people buying a $1,000 CPU and pairing it with a $300 GPU and wondering why their training is slow. Flip that, get a mid-range CPU and put the extra money into the GPU.
So CPU is important, but do not overspend.
Exactly. A Ryzen 5 or Core i5 is plenty for most AI workloads. Get 32 or 64 gigs of decent system RAM, and then put every remaining dollar into the best GPU you can afford. That is the formula.
Second most common mistake?
Not understanding VRAM requirements. People buy a GPU based on its gaming benchmarks and then realize they cannot run the model they want because it does not have enough VRAM. Always check the VRAM requirements of the models you want to run before buying a GPU.
That is solid advice. Any final thoughts for our listeners?
Just that you do not need to wait until you have perfect hardware to get started. The best time to start exploring AI is right now with whatever machine you have. Download Ollama, pull a small model, and start playing. The hardware will come later if you need it.
I love that message. Joe, thank you so much for being here today. This was an absolute blast.
Thank you, Zoe. This was so much fun. I love talking about this stuff, and your questions were great.
And to all of you listening, thank you for tuning in. If you enjoyed this episode, please share it with a friend who is trying to figure out their AI hardware setup. Leave us a review wherever you get your podcasts. And as always, keep building, keep experimenting, and stay curious.
Peace out, everybody.
See you next time.